Another step question then here to do with complex numbers, of course. First thing I'll have to do is a very quick expansion here. Now when we expand this, we of course get, when we group these z's together, of course these adds make 0, each of the 0 is 1. But when you group these, you get something very familiar looking. This is actually just cosh. No, it's not. It's cos, of course, because of the i's. And it's cos over 2, I guess, if you pull out a 2 just to then divide by 2. You can now make it into precisely cos, which is what they're asking for. And I don't think any more explanation is needed than that. Just the easy first part of the question done. So next, we're looking for the 2nth roots of -1. So we're looking for some complex numbers to the power 2n equal -1. Well, we can do, we can raise both sides to the power 1 over 2n, I guess, to look for this thing. -1 we can write kind of intelligently like this for any integer k. And now we can just apply the 2n, right? We can just apply the 2n. We can factorize out. We're just looking for odd numbers, I guess, essentially, when we factorize out the pi I. Then we can apply the over 2n idea. And now, basically, from this line to this line, all I'm saying here is that we can, instead of using any integer k, let's just use the positive ones. And then, of course, to get the negative ones that we previously had, we can just put a minus or a plus here, and that's what we'll say. And if we do it this way, then the roots are always between minus pi and pi, if we do it that way. Cool. Okay, so that's all that done, and now we're being asked to deduce this big thing here, based, of course, on these two ideas that we've just found. So okay, let's do that. So this is similar to what we were saying before. Z is a 2nth root of -1. If that's true, we kind of said that before. In other words, of course, if we work backwards, we get back to here, which is just the left-hand side of this thing over here. So that's cool. So that, therefore, means that the 2nth roots of -1 are the roots of that equation there. They're just the roots of this. But of course, if they're the roots of that, then you can write them as just, like, you know, if 1, 2, and 3 were the roots, then it would be z minus 1, z minus 2, z minus 3. We can write these as the product of z minus all of the roots. But we just said that all the roots are this plus or minus idea, e to the plus or minus this thing here. So one of the brackets is going to have essentially all the pluses in it for all the different k's from 1 to n that we're going to pick. And the other one has all the minuses, again, from k being 1 to n. This is why we changed it to be this plus minus idea, so that we could write it like this and only run from k as the positives in our product expansion thing here that we've got. But okay, this is where we use the previous idea, where if we expand this out, notice, well, we don't even do to expand it out, right? Just look at this object here and look at this object here. Of course, if we just replace theta with this whole complicated business up here, we end up straight there, and so therefore it's just going to be equal to this. Which of course we can then say is essentially just what we're being asked to show. So that's good. So we're done with that part as well. Okay, so that's that done. So the next part, is by substituting z equals I, show this thing here. Now, presumably we're going to substitute into this object we just made, because that's how step questions work. We're going to assume n is even, but we don't really need to know that right now. We're going to assume that a little bit later on. If we put in z as I, we end up with this. Of course, some of this ends up being quite nice. I is squared is -1, which cancels, which is good. There's going to be a lot of that coming up. And then, of course, here, you can say in brackets, maybe this is I squared to the n, because you times the things together to make 2n. I squared is -1, so that also goes there as well. Now, a couple of things going on this next line. Firstly, if n is even, which we're supposed to assume it is, -1 to the n is just 1, so 1 plus 1 becomes the 2 here. Now, over here, this is just 2 lots of I cos whatever, times 2 lots of I cos whatever for a different k, times 2 lots of I cos whatever for a different k, and so on. All those 2's can essentially factorize out, just like they can in the sum, but also so can all the minuses, minus 1's, and there's n of each of them. So those, this -1 and this 2 have both factorized out of the capital pi, the product thing that we've got here. So okay, that's all cool. We can now do some separation still. N is still even, so this thing here is still just +1. This thing here, again, we can do the same thing we did up here, where maybe write n intelligently as 2n over 2, and then break it up into I squared times n over 2. I squared is -1, and then we get this kind of object down here being formed. And I only did that because, again, we're always keeping our eye on the answers and seeing that that's the kind of thing that we're supposed to be doing here. And then over here, again, keeping your eye on the answers, seeing if you can still try and get here as quickly as you can. When we move this over to the other side, it doesn't actually change it, right? Because, this can either be a +1 or a -1, essentially. So if it goes to the other side, it's just whatever it is still. Like if it's a minus, then it just becomes a minus over there. If it's a plus, then it's still a plus over there. So that doesn't change. Now this one obviously doesn't matter. And this is 2 to the 1 divided by 2 to the n. So that's 2 to the 1 minus n here. And that will be there. And that's pretty much exactly what we've got over here. So that's good. So now we just need to say, well, okay, what happens to get to here? Well, it's just what the summation, not the summation, but the capital pi actually does here. The product is what it does, right? When you put in k as 1, you just end up with a single pi here. When you put in k as 2, you end up with 3 pi. Put in k as 3, end up with 5 pi, and so on. And so we get the desired result up there from there. And now we're into the last part, and it says, show that when n is odd, we get this slightly more complicated looking result. And at some point we need to be using this idea here. Now we notice this is something we already got, so we probably want to use it pretty much straight away. So okay, let's think about that. And probably the easiest way to do this question is to see what happens for some low n, so n is 5, and then just apply it and see if that works for any n, right? So let's just think what happens when n is 5, because we can write out this product here for when n is 5 without too much effort. So we write it out like this, and then we notice this really key thing here, which is cos 5 pi over 10 is just cos pi over 2, and cos pi over 2 is 0. So that's going to go away, and even better, that makes this whole bracket z squared plus 1. And then they've told us, very helpfully, that the left-hand side of this whole thing should have a z squared plus 1 in it, which is, of course, going to cancel. So we can cancel those out and be left with this here. So I think we're on the right tracks here. We can also think maybe, if n was any odd number, would that middle term still work? Well, if it's a 7, doesn't work so well, like if n was 7. But if n was 7, there'd be a 1 coming earlier that might be helpful, I guess. But of course, if n was 7, the bottom one then would be a 14, actually, wouldn't it? The bottom would be 2 times 7 for 14, and then it would still be a pi over 2 somewhere, just somewhere else. So that seems like that's a step that might work every time. We'll get to it when we get to it, though, but just keeping that in mind. Let's just run with this n equals 5 idea a little bit longer. So now we can do the same thing we did in the previous part, right? Where we let z equal I. But I mean, if we did it in the previous part, we should probably do it here as well. And that's good, right? Because the I squareds and the 1s all cancel just like they did before. So that's very helpful. Of course, when we put in these, we end up with some stuff over here, which I'm sure you can work out. And we end up down here. We can write this, I guess, as 5 times, of course, this is 5 times 2 to the 0. So when you divide by 2 to the 4, you get 5 times 2 to the 0 minus 4, which is the same as 1 minus 5, right? I'm essentially just moved the 4 over to me 2 to the minus 4, but then written it as 1 minus 5, because I'm trying to write it like this and justify that I can just make 5 any odd number I want later. So okay, we end up with this here. This right-hand side is really not doing anything complicated at all. I factorized all the 2's just like, and the i's and the minus 1's just like we did before. Where do we go from here? Well, it turns out that cos pi over 10 and cos 9 pi over 10 of course have a special relationship because they're symmetrical around pi down here and 0 over here. One's just the plus version and one's the minus version. So cos 9 pi over 10 is just minus cos pi over 10, which makes this minus cos squared pi over 10. But exactly the same thing is happening with these two, because again, they're symmetrical around pi over 2, essentially. And then 2 minuses cancel and make a positive, and we end up with this here. And it seems like the whole thing works for n equals 5, because of course we could write 3 as 5 minus 2, and then this is a 10 here. So that seems like it works pretty well. So let's just do the whole thing where n is odd and just hope that it works as well, and just copy all of our working. For PowerPoint, this is super easy for me, because you just copy and paste every slide, but just replace stuff with n's. And we'll notice at some point in this product, like we were saying before, at some point justifiably these n's go away and we end up with cos pi over 2. So in 5 it was 5 pi over 10, and with 7 it's 7 pi over 14 and so on. But it's still going to go away, which is fantastic, because that still means 1 plus z squared will cancel with 1 plus z squared. And we'll be left with this same kind of thing we had before. A little bit more complicated because obviously we have to go further. We're going to the last term over here. But okay, now we're going to let z equal I, because that's what we did last time as well. We do need to be a bit careful here as well. Obviously all these things cancel and just leave us with a bunch of 2i cos whatever with some minuses in as well, which we'll factorize out as we've done a couple of times before. Let's be a bit more careful over here, because the numbers go 1 to I squared to I to the 4. So that's 1 to the minus 1 to 1 to minus 1. They must go 1 to minus 1 because the I power is increasing by 2. I squared is minus 1, so it's just changing the sign each time. So it goes 1 minus 1, 1 minus 1, and so on. But the signs go minus, plus, minus, plus from up here. So the minus is always attached to the -1, and then it goes +1, and then it goes minus, -1, and so on. So it's just 1 minus -1 plus 1 minus -1. And so that's just ones adding together, and there's n of them, so that's just going to be n over there. Now over here, done a couple of things. Factorized out all the 2's and all the -1's, and even all the i's as well. Now, n is odd, so n minus 1 is even, so that's just 1. And we'll leave this bit alone here. We group the... sorry, we'll also write I as, or I to the n minus 1. That same thing we did before, where I is essentially -1 to the half, I guess. And then we can write it like this. And now over here, we can say that the causes go together the same as they did before, right? The first and the last cos go together. One's just a minus of the other one, and so on. We can write down the rule if we really want to for that. But it's the same thing as was happening before. We'll just assume that that stays. And then we've got a bunch of minuses. Now, how many of them have we got? Well, when n was 5, you had 2 of them, right? You just had this one and this one. And 2 is 5 minus 1 over 2. If n was 7, you'd have 3 of them. You'd have the 1, the 3, and the 5. And 3 of them is 7 minus 1 divided by 2. So it seems like we've got n minus 1 over 2 negatives here. So we'll factorize those out. But then, of course, when we add these together, they just... I mean, you can think of this as just this thing squared. So whether it's a 1 or a minus 1, when we square it, it's going to be a 1, right? So that whole thing is just a 1. And I think I ran out of space to write it. But if it is just a 1, I think I probably could have just not written that there. But if it is a 1, then you end up with this relationship exactly that they were asking for. And that's the whole question. Thanks for watching. The last of the step questions in the complex numbers booklet then. So we're asked about complex numbers representing the vertices of an equilateral triangle. So in other words, it looks a bit like this maybe, a triangle like that. Of course, it could be labelled the other way around. So instead of going alpha beta clockwise like this, it could be alpha beta gamma anti-clockwise, a bit more like this. But sure. The first thing we should probably do is shift this so that one of the points is on the origin. It doesn't really matter which, but if we shift it so that B is at the origin, or beta I should say, then essentially we're just taking away beta from all 3 points. So like beta minus beta becomes 0, and then this point will become gamma minus beta, and then the other one alpha minus beta. And again, we could do that with the anti-clockwise one as well. It doesn't really matter. And at this point, what we can say is, for this to be an equilateral triangle, we can come up with these two statements here. Either gamma minus beta is equal to alpha minus beta, and then times by this number. Now, this number is just pi over 3 I, because it's representing a rotation of pi over 3. In other words, because this is an equilateral triangle, it must have an angle here of pi over 3, of course. And so we're rotating gamma minus beta pi over 3 to become alpha minus beta. Or, in the case of the anti-clockwise case, rotating it the other way. Now, there's no more scale factor here aside from just this rotation, because, of course, equilateral triangles also have the same length on every side. So this is a necessary and sufficient condition because we're rotating the right angle and we're also not changing any of the lengths. So it's necessary from the diagram because of course it needs to be 60 degrees or pi over 3 and it needs to have the same length. But it's also sufficient because any isosceles triangle that has angle pi over 3 in between the two lengths that are the same is also equilateral. So this is necessary and sufficient, so we're good with the if and only if thing. Now, where have we seen things like this thing can equal this, or this thing can equal this before? Well, when you go all the way back to like quadratics, you have like x minus a into x minus b equals 0. X can be a or b, right? So we can do the same thing here. We can set up a quadratic such that this minus this into this minus this is 0, right? This is our only if and only if condition, right? We've got two roots here. We've got this minus this root. Not sure why we put this green, but whatever. This minus this one is either 0 or this one is 0 because it could be this one instead, right? So we've reverse engineered these kind of brackets from the statement that either this must be this or this must be this. And now we can expand this out. I think that's why the colors are here. Help you to see how I've expanded that, I think. Useful that these two things go away, of course, because they add together to make 0, so each of the 0 is 1. After you do a bit more collecting of the correct things together, you end up with something that looks a bit like this. And then we can collect more things together and factorize to look like this. And this should hopefully be very recognizable. This is the formula for cos, I think. E to the x plus e to the minus ix over 2. So that's cos of pi over 3. But cos of pi over 3 is just a half. So that cancels out 2, and that's super nice. And we end up with this, which further reduces down to the thing that was required. So a tricky start to this question, but we've got what was required. And now it says show that the roots of this represent the vertices of one of those equilateral triangles if and only if this. So okay, we've got alpha, beta, gamma be the roots of that equation there, so that we can therefore write it as z minus alpha, z minus beta, z minus gamma. So that's cool. Okay, so, well, okay, we can expand that out, and this is just kind of roots of polynomials things for people who have done that chapter, so that's not too complicated. At this point, just note that if you square a, you of course get alpha squared plus beta squared plus gamma squared, and then 2 of each cross term, and the minus just cancels with itself when you times it by itself. So just note that as well. And now we can just put this together, right? Like we can show, firstly we're showing an if and only if thing, right? So we'll split into, this will be the if and this will be the only if. So if alpha, beta, gamma do represent the vertices of an equilateral triangle, well then they follow this rule up here by the previous result. And we can write this really intelligently. We can say that let's write it as close to looking like this as possible. So let's just add in 3 copies of this, this, and this everywhere, only to then take them away afterwards. And now we can make this, because all I've done is here, added copies in just to take them away, because this of course is now just a squared, and this here is just b. So we end up with a squared minus 3b equals 0, which means a squared equals 3b as required. And now the only if, so now we start at the a squared equals 3b, and we let the thing be the root. So now we're essentially now showing that they are in an equilateral triangle, I guess. So we start with this, we move it over to this. This is essentially just working backwards from what we just did. So this side was actually the easier one to do first, because then you could have got this more difficult step out just because you were doing this backwards instead. But you end up at the same result here, and because this is an if and only if statement itself, that means that the 3 points are in an equilateral triangle by the previous result. Okay, and we're at the last bit actually, surprisingly, here already. So we've got a transformation here, so let's put that transformation in here. That seems like a logical thing to do first. So let's throw that result in. We end up with this here. We've got a bunch of algebra to do here, but it's not particularly complicated. You just kind of do it. Divide by p cubed in order to get a 1 here as required. And then this thing here is a, this thing here is b, and this thing here is c. And we'll call that star star, I guess, where with a, b, and c in the right place. And now we need to take that and show that they, if these things, if the roots of these things are in an equilateral triangle, then these ones are also, is what we're being asked to show. So let's suppose that they are, which of course means that a squared equals 3b by this result, the second of the 3 results that we're sort of doing today. So all it remains to do is if to show that this one also does it, we just need to show that this coefficient squared equals 3 lots of this coefficient, because of course that's just the rule from here, whatever those coefficients are. So all we need to do is show that a squared equals 3b. So let's take this big a squared and square it, of course, and work it out. It ends up being this. This is one way of writing it. There's a bunch of ways you could write it. Let's take the right hand side. We don't really need to make that into 3b. We could just separately look at 3b, which is 3 times this, of course, and write it out like this, and then of course factorize out, I guess, 3 more p's just to make it look like the first result, and that's not what I've done. What have I done here? Oh, I've replaced 3b with a squared, because we know that the first result holds because it says if star, if the things that are there, so a squared equals 3b, so replace that with a squared, then I think take out those extra extra 3 p's, and you end up with the same result. So yeah, that means that we have a big A squared equals 3 big B squared, and that means, of course, that star star also represents vertices in the equilateral triangle by the previous result, and we're done here.